Hello everyone, welcome to this video. So in this video, we are going to learn very important topic called PCA, Principal Component Analysis. See, PCA is very important tool. Okay, so in this video, we'll try to understand first why we need PCA, and then we'll talk how it performs and how mathematically we are able to build the PCA. So PCA means Principal Component Analysis. And let me first explain why it's important, and then we will see how mathematically we are able to build PCA. See, first let's try to understand PCA as a box. Okay, suppose this is a PCA and it's a box. If you have a data, okay, and maybe in this data there are total maybe 100 feature. So F1 till F100 feature, and maybe sample is like 1 2 3, maybe 4,000 sample. So the shape of this data will be 4,000 into 100. So basically there are total 4,000 sample in this data and 100 feature, but I want maybe top 20 feature. I don't want 100 feature. So I want to reduce the feature dimension. See, there is another method where we selecting the top feature. Maybe you are using, you know, different methodology to select top feature. Okay, so maybe you are using random forest and try to get the top features. But here we are not using that. We will reduce the dimension top 10 feature. Those features will not from this feature. We will create top 10 feature. So we will let you know. I will let explain how mathematically it will make sense. Suppose I am looking for top 20 feature. So if I pass this data to this box in output, I will have a data where there will be F1, F2 till F20. So there will be 20 column, but sample will be same. So like again, I have the output data will be 4,000 cross 20. So the number of sample is still same, but column will change. Now I don't have 100 column, I have 20 column. But important news is that this feature F1, F2 is not same what is there F1, F2 and F20. This is different. If you check the value, that is totally different. So let's write someone maybe A1, A2 and A20. So let's not use the same feature name. So this is a different feature, right? And these are nothing but your principal component. So however it is building, it is using this feature and try to generate this, you know, using the math. I'm going to explain the maths behind this, how we're able to reach here from here to here. Okay, so we'll see the math, but this is basically the PCA. Okay, so first let me show you one simple, uh, box. We'll pass the data and it will do like this, and then I will come again and we'll see the maths. So let me show you first data and we'll try to see this full notebook. But right now first, let's see this. Suppose you have this data. So here you can see there are 20 row, sorry, 10 row and 4 column. And suppose I am using a PCA as a, right now just think as a black box. We'll see this how to, how maths works behind it. But anyway, first let's see run this. So I am just importing the PCA and standard scaling to first scale the data, and then I will pass my data through the PCA black box. Okay, don't worry, I will share this notebook, so no need to worry of the code. So now we have the standard scaling. So I'm first scaled out this data, and then I'm taking a box, PCA box, passing here in component is equal to 2. So I'm looking for top 2 feature only. So if I run it, now I get this data. If you check the shape of this data, if you check the shape of this data, here you can see we have the same 10 row, but now I have 2 column. Here it's 4 column. If you see the number first 2.5, but now it's 1.5. So you can understand this. This is not the first column, right? It is generated column. So we are generating using these feature. Okay. So this is right now what we are doing. We just understand why PC is important to reduce the your feature. So if you have 1,000 feature, you can reduce to maybe 20, maybe 100. Okay, top 100, top maybe 100 feature if you have 1,000 feature, right? So this method is very important, very useful whenever you are dealing with high dimension feature. You can reduce the feature using this methodology. Now, and it's very important to understand how actually mathematically it works. So till now, I believe you are able to understand as a as a uh, you have the better intuition why we need to learn PCA. So basically, if you have a high dimensional data, you want to reduce it, you can use PCA. I believe you are able to understand till now, right? Now let's see how it works. So for that, suppose I'm plotting here data. Just see carefully. I have suppose 2D data and I plotted this x and y. See carefully. And maybe my data looks like this. So let me change the color. Maybe my data looks like this. Okay. See carefully. So this is my data. Okay. So see carefully. If I'm taking maybe point this point, so this is a change in x and this is change in y. So basically the point is like here, this is x axis and this is y axis. So this is basically axis. Suppose just change your view, and suppose we are taking this as a axis. This is a this is as a axis. Okay. Maybe this is my uh u axis and this is my v axis. Now see carefully, if I change my axis, like first I have x and y, right? Now I just change my axis. So what will happen? Now if you see in this theta, very, very low, low change in B, but still there is a high change in U. If you see this point, right? This point. So there is a this much change in U. But how much change in V? Very small, right? So if you see variance in this data mostly around like shifted on U, very very less on V, right? But if you see on XY, it is there for both X and Y. But if you change the your just to change the your basis, now you can see how change in the data looks like. Like if you check any point, suppose you take here, so there is this much change in U but very less change in V. If you see here there is a small change in V, but very small change in V. There is a change in U. So if you take here, maybe same change in U and V, but still there is change in V. But mostly data, you know, there is a most change, just in the U direction. Very less change in the V direction. So why I'm explaining this? Very, very important. Now, this is actually PCA. So what we are doing, if we have a data in n dimension or maybe any dimension, what we try to see, we try to shift our, the basis basically to, we are just changing the basic like that. The most variance we are going to cover. Okay. So that's why if you see, if you have like here you can see we have two basically like you have a two axis, again you have a two axis. Suppose you have a n dimensional data, so still we have a new n n dimension, the same number of dimension, but the first dimension will have the maximum variance, second will have the lesser than the first one, third one will be even lesser than that. Okay. So and here you can see this is my, if this is my first component and this is my second component, variance of first component is very very high if you compare with PC2. Similarly, if you have a n dimensional data, so we'll have how many component? PC1, PC2, PC3 till PCN. But don't need to take PC till PCN. Why? Because the maximum variation will be have the PC1, then PC2, then after PC3, maybe till PC10 we are able to cover almost 98% variation. So we can at least going to remove the last components because maybe they will have very low amount of variance. So basically we are looking for the information and we are able to get the information, right? So till now I am able to, I believe you are able to understand why PC is needed. So for dimensional reduction, and you know why dimensional reduction needed, because if you are dealing with high dimensional data, it's very, very needed to, reduce the dimension to you'll get better accuracy, right? Now here what we see, we try to plot the data and try to understand if you change the axis, if you change the basis, definitely some maybe like here you can see this U has almost 98% variation, maybe V has very 2% variation, so we can at least reduce you can leave the V, right? So in that case, uh, we are able to convert into 1D. We have to read data, but we just converted into 1D if you're taking U and remove B. Similarly, if you have n dimensional data, we can convert like that, and we'll try to find maybe top 10, top 20. So this is just a graphical representation. Now let's try to see mathematically how we are able to deal and how we are able to convert it. Okay. So maybe you are not you're not able to recall all the maths, like because here we're going to use some mathematics background. But if you don't know, be there. I will going to explain parallelly, mathematically and theoretically, so you are able to understand how it is working, right? So in real work, when you are doing a PCA, what I already saw in that way, you just loading the PCA, giving the how much how much component you are needed, and passing data, you'll get this, right? But mathematically understanding need little mathematical background. If you don't have, be patient, you are able to still able to understand how math works behind it. Okay, so let me explain you. So suppose we have a data x. Okay, so what we are looking for, we're trying to find a direction, maybe w. Okay, so w is a vector. So find a direction W such that variance of the data projected on W is maximized. So what we're trying to looking for, we try to find a direction, we try to find direction where such that variance of the data projected on W is maximized. So you're always looking for maximum variance, right? So let me explain you. So see, if you x dot w, basically this is nothing but your projection on w. So x is data and we are just projected on w. So if you see the variance of xw, we always looking for maximum, right? We always looking for maximum of it. I believe you are getting the point. So we want to maximize this what projection of that area, so that direction. So w is a unit vector basically. If you see, this is a condition like w transpose w is equal to 1. So we are looking always going for a unit vector because we are mostly trying to get the direction, right? I'm going to explain why this is related to unit vector. So let's see, suppose take a variable maybe z, and we're saying z is equal to x dot w. Okay, so this is basically the projection on W. So this is the variable right now considering. Okay. One thing which is very, very important, that your X is zero centric. Okay. So whenever we start building the PCA, first what we do, we try to get X minus mu. So we just make our data to zero centric. This is very, very important. Okay. So now see, let's try to see this. So basically what you're looking for, we want to variance of Z, and that we want for maximization, maximize, right? Now I believe you know that what is the variance formula. If generally it's x minus mu, right? And x mu transpose, but if mu is 0, so basically x dot x transpose, right? So definitely it's 1 upon x minus 1, right? So this is variance formula for you know so let's do this. So if we want to maximize this, variance of Z will be what? 1 n minus 1 Z transport dot Z. So this is our variance, right? Let's break it down. So we already know this, 1 upon n minus 1. What is Z transform? Nothing but your x w transpose dot xw. So why it is, from where it is coming from? Here we take, we just take a variable Z. What is this? This is nothing but your you know like your directional vector. W is nothing but a unidirectional vector, right? So if you want to calculate the projection on it, just you have to multiply with your real data, right? So x multiply w. So now this is your we are looking for to maximize this. Okay. Now see carefully. If I write like this, 1 upon n minus 1, okay. So even we can write like so, na, if you open this, what will happen? W transpose, then X transpose, X W. I just open this transpose. Now I can write like this, na, W transpose 1 upon n minus 1 X transpose X W. And see, this is the formula for what? Variance, no? So this is the X. So it means this is W transpose. This is basically your variance. This is W. So this is what? This is variance of what? Your real data. That is your X. Are you getting my point? Let me start again. Maybe if you don't have mathematical background, don't worry. See this. What is happening? We know this. We want to get the direction where we have the maximum variance. So this is basically your x into w, because w is just your unit vector, right? So we say this is the projection, that is z x dot w. Now let's calculate the variance, that is variance z, and it has to be the maximum. So first what we do, we just open this variance. So 1 upon n minus 1 z transpose z, and we know that z is equal to x dot w, because this we just assume that this is z, okay, projected on w, your unit vector. Now just open this and we got this one. So here it is w transpose your unit vector, right? This is your variance, and this is again a w unit vector. Now we already know there is a one condition, w transpose w is equal to 1, and this is very important, right? It's not like only a condition, it is very very important. I'm going to explain you. So why it is? Because PCA is fundamentally about finding a direction. Okay. So PCA is fundamentally about finding a direction of maximum variance, not the magnitude of the direction. So we are not looking for magnitude of that direction. We are only looking for the direction. That's why we are taking as a unit vector. Okay. Now we want to maximize this, right? We want to maximize this one. We want to maximize this while while this condition. So we want to maximize this, but with this condition. So for that, let's use the Lagrangian to maximize this. So if you don't know, don't worry. I will reaching to the main result, but anyway, I'm just deriving this. So let's take the Lagrangian here. Okay. So this is your WTCW minus lambda, and this is your relation condition, W transpose W minus 1, right? If you take derivatives of this, okay, if you take derivatives of this, so do you know what will happen? 2c, sorry, 2cw minus 2 lambda w is equal to 0. So basically cw is equal to lambda w. I'm just keeping 2 3 lines because that is not important. So I'm just trying to explain you main thing. So where we are reached now, just focus on this, you know. So you know, so here I'm just writing one thing, and that I will going to use here. So whenever you have like a b e b, and your if A is a symmetric matrix, okay, if A is a symmetric matrix, always remember V is a eigenvector. V is a eigenvector of A. So always remember this. If you have like this, if A is a symmetric matrix, B is a eigenvector of A, right? And this E is just a magnitude. Okay. So see here, because we already know C is a symmetric matrix. Why C is a symmetric matrix? Because it's nothing but covariance. Covariance is always a symmetry matrix. We already know that, right? It means this is nothing but eigenvector of what? Variance of x, right? So W is nothing but eigenvalue variance of this. And this is your just a scalar value, eigenvalue. Okay. So now I think you're able to understand. Let me restart it again from where we started. We started from here. What we see that if you want to calculate a principal component, so what we are looking for, we're looking for find a direction W, a unit vector, such that variance of the data projected on W is maximized. So we always looking for that. So first we calculate the projected on X, and that is my unit vector. Then we calculate the variance. So we see this is Z, so we write variance of Z, and then we write the variance formula. Then we write Z value, so we got this one. Now we have to, so we got this one, and this is because we just open it, so we find that this is basically nothing but variance matrix of X, right? Because from here we replaced it. Now, because we want to maximize this, so for that we used a Lagrangian equation, and there is a condition here. Okay, and I told you why this condition is needed, because PCA is fundamentally about finding direction of maximized variance, not the magnitude of the directional vector, right? So that's why we use the Lagrangian equation. We write here, then we differentiate and put it 0 to find the maximum value. So we just do this and define the equation. As we know that whenever you have a relation like this, and if A is a symmetric matrix, B will be the eigenvector of A. So in the similar way, because our we already know that C is a symmetric matrix here. Why? Because this is a covariance of X, right? So that's why W will be eigenvector of what? Variance of X. So first we calculate the variance of X, then we will calculate eigenvector, right? And then we have the lambda is basically your eigenvalue. So this is nothing but your magnitude. So now we got the W. So if you want to calculate Z, we have to multiply X into W and we'll get the Z what we are looking for. So now let's calculate similarly, okay? Because prior what we did, we just used the library. So maybe you, and now you understand the maths. Let's do the similar thing here. So let me go one by one. So this is my data, okay? First, let me calculate the mean, standard deviation. What I did, I just make it centered, okay? So this is my center data, okay? Now, here I just calculated correlation to check it, but let's calculate the covariance, which is very important. So this is my X covariance. Why we need X covariance? Covariance because I explained, na, we'll calculate what? Here we see, na, if you want to calculate the W is nothing but eigenvector of variance of X. So first we calculate variance of X, then calculate eigenvector of X. Why we need W? Because we are looking for Z, and Z is nothing but W into X, right? We know that. So let's do this. So first we calculate the variance. So this is my variance. Now what we do is calculate the eigenvalue and eigenvector. So we have the eigenvector. Now what do you need to do? So we have the eigenvector. Here we can see. So from where we got the eigenvector? From where we got the eigenvector? We calculated the covariance, then we calculate the eigenvector. So this is nothing but what? This is W, what we are looking for, right? Now let's multiply this W with Z, with this, sorry, with the X, so we'll get the Z. So here, suppose we take two PCA. If I if I if I take all PCA, okay, so let me write this. So here we got this four value PCA1, PCA2, PCA3 and PCA4. But suppose I'm looking for only PCA1 and PCA2, I want to reduce to 2. So what I will do, I will take only two eigenvector, first and two, second. So in that case, I will get this. So here what I'm doing, I'm taking this, and then I'm doing this matrix multiplication with the X data, and we got the PCA, right? So this is basically PCA. So even if you compare with the data, you will get the similar data how what we get through the library. If you compare with this, you will get the similar data what we are doing through the library. Okay, so let me explain it again. Let me explain it again what we are doing, and we know this now. We are able to understand mathematically and intuition why we are doing this. So let me explain why we are doing this. Because you want to reduce the dimension. This is first why. How we are doing this, we know that because we are always looking for what, we are always looking for projection on the unit vector and the maximized variance, right? So in that direction we need the maximized variance. So for that what we did, we calculated taking any unit vector, then we multiply with x to get the projection on that. We say it is z. Then we calculated variance of that z. So when we calculating variance of z, when we calculated variance of z, here you can see, when we calculate variance of z, we open this z is equal to your, this is variance formula, and then we open z is equal to hw. So we got this actually this equation. C is basically your variance of x, right? Now we want to maximize this with this condition. So we write a Lagrangian equation, and then we do the differentiation and put the is equal to 0. So you got this equation. And we know this, if C is symmetric, because C is symmetric, because it's a covariance matrix, and always covariance matrix are symmetry matrix. So if it is symmetric, it has to be what? Eigenvector of C. If it is satisfied like that, that's why it's eigenvector. Now we did the mathematically, and we are able to generate the PC result. Okay, so I believe you are able to understand, what is happening and what is not, right? If you can see, I'm saying that it is symmetric. Here you can see this value and this value is same. This value and this value is same, right? This value is same. Basically, symmetric means Aij is equal to Aji. So in that case, if you compare it, this is always a symmetric matrix. So this is a covariance matrix, this is symmetric matrix. That's why that time W become the eigenvector of this, right? That's why we calculated eigenvector of it and multiply with x, and we got the real value. So this is about the PCA. I think you are able to understand why we need to do PCA and how it is actually, you know, you are able to solve mathematically. If you're not from mathematics background, maybe you're not able to understand, but at least now know that why we're calculating the eigenvalue and eigenvector. Sometimes people know we need to calculate eigenvector, but they don't know how it is coming, right? So in this derivation, I actually try to explain you. Definitely, I skip some derivation, but I just want to give you the intuition. Real time, anyway, you are going to use the library where you are providing your data and giving the how much number of how much components you are looking for, and then you can calculate the variance, right? So in this way we are able to solve the you are able to generate the principal component, right? And it is very helpful. So this is the scratch code, but when you are doing a real way, you just passing through this, we're just giving the how much component are needed, and it will provide you the results. So I believe you are able to understand. Thank you so much for watching this. If you are like able to understand and it is helpful for you, please do subscribe and like my channel, like this video also. Thank you so much.